Hi class, I want to continue on with the last video where I was looking at CLF3 and my iPad died on me in terms of battery. So I want to continue on from there. We had the CLF3 that I was discussing, and I was trying to tell you the valence electron and the electron method, whichever you want to really follow. Valence electron method. And I wanted to show you how we can use that to essentially determine the structure and what the vsepr would be. So realize chlorine has 7 electrons, 7 valence electrons, and each of the 3 fluorines is going to bring in 7 electrons of its own. So total you have 28 electrons in place. Now, we know rule-wise fluorine is more electronegative as compared to chlorine. So chlorine is going to be your central atom, and surrounding that you're going to have the 3 fluorine atoms. Now, first you would take the time to place one electron surrounding, one bond, surrounding the chlorine to form 3 chlorine-fluorine bonds. And in that sense, you have utilized essentially 6 electrons in that process. So 28 minus 6, that is 22. And now if you try to place these 22 electrons around the elements, that's 6. These are 6 again. These are 6, so those are 18. And I still have 4 more electrons to go. So that's 4 electrons, and those are going to stay essentially on the central atom chlorine. So if you think about the vsepr formula for this, it's going to be AX3E2, where the E stands for the lone pair of electrons, the X stands for the electron groups for the fluorine. So these are the bonding electron groups. So realize 3 plus 2, that is 5. So in terms of the geometry, it's going to be the TBP geometry. Whereas if you consider the shape of the molecule, you have the Cl. Recall from class that you want to give the lone pairs essentially, let's put it this way, the equatorial position. And so fluorine would be right here. One fluorine will be on top, the other fluorine will be at the bottom, and so this will look like a T shape, like a T junction on the road. Hence this shape is also called as a T-shaped molecule. Now realize in cases like these, the electron accounting method sometimes may not give you the correct number. So valence bond in that case is a little bit more reliable, because as you can see the CLF3, you can perhaps see that you need to complete octets of all 4 of these. That means you need a total of 32 electrons, and you have currently 28. And when you do the math and it comes out to be 4, which when you divide by 2, it will give you 2 bonds only. But you have 3 fluorines already in the system, so that clearly does not quite match up. So, and if you go back to the valence bond method that valence electron method that I gave you a couple minutes ago, essentially that shows you that the structure is Cl with 1 fluorine. And so if you think about how many electrons are surrounding the central chlorine atom, you would see that it is getting 4 electrons from the 2 lone pairs and 6 electrons, so that's total of 10 electrons. So that's the case of an expanded octet. It's an exception anyways in to the Lewis theory. Okay, I want to take the time to talk a little bit about polarity. Polarity is seen in a molecule if you have bond dipole, and in addition to that, your structure of the molecule is pretty asymmetrical, unsymmetrical. So 2 things that you would seek: one is the bond dipole, and the other is the unsymmetrical structure. And so recall from class, the first thing I want you to take a look at is the delta En, is the difference in the electronegativity, is that more than 0.5 or not? Because if it is not, then it's no point looking for the asymmetry, because the molecule itself will be nonpolar. So something like carbon and hydrogen, let's say you are talking about CH4, and all that compound has is the hydrogen bonds, carbon hydrogen bonds in a tetrahedral fashion. And so since there is not as much difference in electronegativity, if you think about the Pauling scale, carbon is at 2.4 and hydrogen is at 2.1. So the difference between them is 0.3, which is less than 0.5. That would mean that this is a nonpolar compound. So the first thing I want you to check is to take a look at the bond dipole and to see if the two elements that are participating in the bond, how far apart are they on the periodic table. And if you do see polarity, then the next thing that you got to check is if those two polarities, since they do have a vector sense, a sense of direction associated with them, you want to make sure that they don't cancel out on each other. So another example of that could be something like SF6 that we discussed last class. Where you have sulfur in the center, you have fluorine surrounding in an octahedral fashion, and what that means is that the effect that one fluorine has in one direction is essentially nullified by the effect on the other direction, and that happens for the entire molecule, which is why I say that if you have symmetry in the structure, it's going to nullify the bond dipoles. On the other hand, let's say we change one of these fluorines and we convert it into maybe a chlorine, everything but the fluorine chlorine, that pair essentially, so the effect on this side and the effect on this side is not going to get nullified, and so this part will definitely show some polarity, and you would say that this compound is polar. So polarity, which essentially is the separation of charges, is dependent on the difference in electronegativity for a particular element in a compound. And the other thing I want you to compare around is the unsymmetrical or symmetrical geometry associated with the molecule. Like I told you in class, polarity will be measured in dipole moment. Polarity is measured in dipole moment. That means higher the value of higher mu means it's a polar molecule. So a lot of times you might be given, let's say 4 molecules. Let's say SF4, CH4, CCl4, and F6, and the question is which of the compounds is polar. So this is an assessment which is testing you at multiple levels. If you consider SF6, I just discussed that the 6 fluorine atoms are in an octahedral symmetrical shape, octahedral, and so they are going to essentially cancel off the effect in each direction. If you consider CH4, you have carbons and hydrogens, not much delta En difference. If you consider CCl4, in that case you do have the bond polarity, but then those are directed towards the 4 corners of a regular tetrahedron. So all of these are going to eventually end up being with 0 dipole moment, 0 dB. On the other hand, if you consider SF4, sulfur it contains 6 valence electrons, and it's going to form 4 single bonds with 4 different fluorine atoms. Each of the fluorine is going to bring with it 7 electrons, so the octet of the fluorine is going to be complete. And you can, if you want to choose, let me just redraw this, make room. You can choose to either draw like a line, or you can draw like 2 electrons. Either of the two is fine. It really doesn't matter. So you can either choose to draw it like that, or you can show it like that. Either of the two is okay. Let me switch that to what I'm used to seeing. and sulfur is going to have two non-bonding electrons, so one lone pair of electrons is present in this particular structure, and it's because of the presence of SF4, which has a lone pair. Essentially, the shape of this particular molecule is going to be seesaw. This is of the kind AX4E. So sulfur is at the center. You have the lone pair, the two fluorines. There's a fluorine here and a fluorine here. Put all the lone pair of electrons. Now envision if there's a kid here and a kid there. So that's how you would see the seesaw shape of the molecule. It's the AX4E type of vsepr formula. And realize that the presence of the lone pair essentially does not allow cancellation of one side to another, and that is the reason that you would say that this particular compound is going to be polar. In general, you would see anytime that you have lone pair other than square planar, in which the lone pairs could be right opposite to each other, and it could be a symmetric structure, such as the case of xenon tetrafluoride, XeF4, in which Xe is at the center. There's a lone pair on top, a lone pair at the bottom, and you have the 4 xenon fluorine bonds. In this case, you would see that it's a nonpolar structure, even though there are lone pair of electrons that are present on the central atom. But other than that, anytime you have a lone pair, essentially it does cause asymmetry in the molecule, because of which polarity is induced. What I want